If we have a vector v in two-dimensional space, then we have the inner product of v with itself is the square of its norm, which implies norm v is equal to square root of the inner product of v and v, and this holds for all vector v here. Now suppose we have two other vectors x and y in that space, and without loss of any generality, we can choose them in such a way that v is the vector representing the difference between them, that is v is equal to x minus y. And this assumption is relevant as v is an arbitrary vector. Now let us consider the coordinates of x and y be x1, x2 and y1, y2 respectively. Then the coordinates of the vector representing x minus y is x1 minus y1, x2 minus y2. And eventually, this is the coordinates of the vector v. From these relations, first of all, we have norm of x minus y and its square is the inner product of x minus y with itself. Here, using the bilinearity of inner product, we get this. Now again, using the relation of inner product and norm and symmetricity of inner product, we get it as norm x square plus norm y square minus inner product of x and y, and again minus inner product of x and y, and that is norm x square plus norm y square minus 2 times inner product of x and y. And using the coordinate representation of x minus y, we get norm of x minus y and its square is equal to norm of x1 minus y1, x2 minus y2 and its square. Now using Pythagoras theorem, which is discussed in our previous lecture, we can express it as x1 minus y1 square plus x2 minus y2 square. Now just by applying binomial theorem and rearranging them, we deduce the expression as x1 square plus x2 square plus y1 square plus y2 square minus 2 times x1 y1 plus x2 y2. That is basically norm of x square plus norm of y square minus 2 times x1 y1 plus x2 y2. So here we get two expressions of a square norm of x minus y, and comparing them we get norm of x square plus norm of y square minus 2 times inner product of x and y is equal to norm of x square plus norm of y square minus 2 times x1 y1 plus x2 y2, which implies the inner product of x and y is equal to x1 y1 plus x2 y2. And this is the relation between the inner product of two vectors and their coordinates. And here, to find out the value of the inner product of two vectors, we don't have to find out their norms and the angle between them. Rather, only their coordinates are sufficient to find it. Now again, if theta be the angle between them, then we know that the inner product of x and y is equal to norm x times norm y cos theta, which deduces that norm of x minus y and its square is equal to norm x square plus norm y square minus 2 times norm x norm y cos theta. Now for simplicity, if we consider norm of x minus y, x and y are c, a and b respectively, then we have c square is equal to a square plus b square minus 2ab cos theta. And this is the law of cosines, which states that the square of any one side of a triangle is equal to the difference between sum of squares of the other two sides and double the product of their sides and cosine angle included between them. By using all these relations, we get inner product of x with itself is equal to x1 square plus x2 square. And since the inner product of x with itself is nothing but the norm of x and its square, therefore we can conclude norm x is equal to square root of x1 square plus x2 square. That is the square root of sum of xi square, for I is from 1 to 2. Here this result is for two-dimensional space R2. And if we generalize this to n-dimensional space Rn, it simply becomes norm of x is equal to the square root of sum of xi square, for I is from 1 to n. However, here all the norms come from the inner product, but not all norms come from the inner product in general. And here, we just have legalized taking the roots, because if we have any given x greater than 0 and n in the set of all natural numbers, then there is a unique y greater than 0, such that y to the power n is equal to x. That is, y is equal to nth root of x exists and is unique. And to express in the coordinate tree language, the basic fact about the dot product is Cauchy-Schwarz inequality.